So if we take a look at the last question, there's some quick changes that I would make to it. Okay? And notice when we go through and do these, you'll notice I'm writing stuff out. Even on the just kind of straightforward, what's the answer? I will write something out. You should always write something down. It helps you when you go back to review. Did I know the question? Right? In which case you can check your work. Did I have no clue what the question was? In which case don't check your work. Probably because you didn't write anything down. But then also don't change your answer. Because if you're guessing, more than likely your first guess is correct. The more than likely is like 55% of the time you're right. Right? So it's not that good, but take the odds. Right? So, in addressing this question, apply the like dissolves like. This is really like forces dissolves like forces. Rule is a horrible word, but approximation. Okay, to predict which of the following liquids is not a good solvent, as soon as I see the not, I would try and box it. If you've got a different color or a highlighter, use it. Okay, this is 68. Okay, is not a good solvent for liquid bromine. Okay, not a good solvent. Well, okay, so we want to bring in some level of interpretation here. Really, what they're asking is that one of these does not mix with bromine. Okay, so not soluble. So I would convert that not good solvent to not soluble. Okay. Well, if I'm applying my like forces dissolves like forces, my not soluble means different forces. Okay. So I need to look and identify two forces. Well, I only have one answer in each of those. How do I have two things to compare? Bromine. So the comparison I need to make is what's going on with Br2 to compare it to everything else. So Br2 has what type of bond? Why is it a non-polar covalent? Same atom to same atom. Non-polar covalent bond means what force? Means what force? Dipole-dipole is polar covalent. This is non-polar covalent. This is our London dispersion forces. Or maybe for that, by that weird name you were thinking induced dipole, which I don't really want to write out, so let's just pretend that those sequences of letters look roughly like that. Okay. So our weakest force. So I would go back to my structures or my answers and now say what bonds and what forces. Okay. So in heptane, C7H16. Those are all non-polar covalent, which means I have London dispersion forces. Oh, the same thing, so that must be the right answer. This is why we wrote out what we were looking for. We were looking for different forces. So since it has the same force, it's wrong. Xylene, C8H10. Non-polar London dispersion forces. Benzene. Water. Polar covalent, which gets us officially our dipole-dipole, which gets us hydrogen bonding. Well, that's different, so that's a possibility. Carbon tetrachloride, polar covalent, which would be dipole-dipole. We actually kind of have a dilemma based off of our analysis. Right? We're looking for different forces. Well, is dipole-dipole different than London dispersion? Yes. Hydrogen bonding was different than London dispersion. So which answer becomes the correct answer? Which one is the most different? Okay. The most different is really asking us, do you actually know the order of our strength of our forces? Where it started with London dispersion, forces at the weakest that went up to dipole-dipole, that went up to hydrogen bonding, which then went up to ionic. That says ionic. If we compare LDF to LDF to dipole-dipole versus LDF to hydrogen bonding, which one's the most different? Hydrogen bonding, which means our answer becomes D, water. Does that make sense? Okay. We have to scaffold all the way through. So for one question, I've got enough work that covers half the screen. That is what you should be looking for. Okay. That's what you should be putting down. For those of you that can skip steps, that's fine. Just realize you now don't have something that you can check or work from later. You're hoping that you're right straight out of the gate. Okay. Make sense? Okay. That's the fully correct approach. Let's say we look at it. Or are we okay erasing everything for the moment? Yeah. Okay. Test taking strategies. Oh crap, I have no idea what the question is about. Largely because some jerk just went through and erased it. So I don't even know what I'm looking at. So now all I have is the answer choices. I need to come up with something to work from. Okay. CHCHCHHOCCl. What stands out as the most different? D and E stand out as the most different. A, B, and C we could eliminate. You're now down to a 50-50 shot with knowing pretty much nothing about chemistry. Okay? So you can take advantage of that kind of approach. If that is something you're going to do, I would do exactly what I just did here. Cover up the question. Because what you have admitted is that you have no clue what you're doing. Don't let some other weird stuff mess with your ability to recognize that you have no clue what you're doing. Take it as a guess, work the best you can through it, and see what you can come up with. Okay? It's not perfect, but use the system you've got. Make sense? Okay. Does that answer your question well enough? Okay. Next. Did I hear 55? 60. So 65, yeast and sugar are added to champagne to give the sparkle of carbonation, also known as a distraction from the question. Under what conditions is the solubility of carbon dioxide gas the greatest? Okay. Solubility of carbon dioxide in what? In what? What is carbon dioxide being dissolved in? There, well, maybe Mike was a bit overzealous to go through and erase that first sentence. What am I dissolving carbon dioxide in? In champagne. What is champagne? Liquid is good enough. Really what we're looking at is water. So I'm looking at taking a gas and I want to push it into a liquid. That's what I'm trying to do. Okay. I could now randomly think of variables that could affect that, but here's where I would kind of cheat and say, okay, what's the question asking me about? I see pressure, temperature, temperature, pressure, temperature, pressure, temperature, pressure, temperature, pressure. So I'm concerned about temperature and pressure. Okay. Pressure makes sense, it's a gas. That's how we measure gases. Okay. So let's start with the temperature. I'm trying to take a gas and turn it into a liquid. What should I do to the temperature? Should decrease, I need to lower it. Okay? And at that point, hopefully we all have that. Temperature is a factor, so A is wrong. B is fine, low temperature. C is fine, low temperature. D is fine, low temperature. Well, that kind of sucked. I could only eliminate 2 answers. Okay? And now I have to evaluate the pressure. Okay, well, should pressure be a factor? Well, how do we measure gases? Using pressure. So is pressure a factor? Yes. Okay. So we're now looking at either increasing the pressure or decreasing the pressure, high or low. Okay, well, what are we trying to do? We're trying to take this gas that is constantly moving around, and I want to force it into one location. How do you force something into one location? You exert a force on it, also known as a pressure. So what are we doing to the pressure? We're increasing the pressure. Okay, we are forcing those gas particles that are free-floating everywhere and saying, stay in one location. To do that, we have to physically hold them there. That means they're going to be pushing out more. So there's going to be a higher pressure. Did you guys ask that? Does that answer your question? Okay. Kind of make sense?
If you're going from liquid to gas, would you go low pressure?
So if I want to now force my liquid to go into the gas phase, what could I do? Well, liquid to gas, I would increase the temperature. What would I do to the pressure? Decrease the pressure. Okay? So if we think about space, okay, what happens to our liquids as we go higher and higher in elevation? What happens to their boiling point? It gets lower and lower and lower. Why does the boiling point get lower? Well, the lower pressure means the liquid is trying to jump into the gas phase quicker. It needs less energy. Okay? So pressure and temperature are both controlling the phase change between the gas and the liquid. Okay? So when we go to higher altitudes, we have to cook things longer. Why do we have to cook them longer? Because we're boiling or cooking effectively at lower temperatures. When we're cooking something, we're looking at boiling of water. Well, if water boils at a higher or a lower temperature, we're getting into a lower temperature for our system. We typically have to cook longer to account for that difference. Okay. Should we try the, oh crap, I know nothing, what can I do?
Yes, always.
Okay. Whoops, deleted, showed too much. If I really have no clue what's going on within this, it's going to attempt to go through and look at those. I see 3 answers that are all mimicking the same thing, low temperatures. And this kind of a system where it's not select the best thing, they're potentially trying to get me to confuse. Okay, so if all 3 of those are the same, the one thing changing is looking at the pressure, I would make the argument BCD is what they're asking for, which would then mean E and A would disappear. Okay? Which is kind of the inverse of what we just did with the previous question. Okay? But it's coming from where do we see a difference? In BCD, yes, they say all low temperature, but they also have another characteristic that obviously changes. In that first question we looked at, we eliminated the first 3 answers because there was no difference between them. Right? Like low temperature. But then there was literally no difference between them. We didn't have a way to evaluate and differentiate those answers. Okay? Here we do have a way to differentiate those answers. So we find the commonality, and then we look for the place that we can differ. Okay? This isn't as nice of an elimination because we're now down to 3 answers, deciding between high pressure and low pressure. We could try that jump, look at the pressures. High pressure, high pressure, high pressure shows up 3 times. High pressure is probably a good answer. Well, where does low temperature and high pressure overlap? Oh, snap. The correct answer. Okay. We're guessing, but we're trying to use the information buried within the answer to guess our way through it. Okay. That's a tip-off that you can do on most multiple choice exams, particularly if you've got 2 choices. They're going to try and put the most common answer in there for both pieces, and only one case will they overlap to get you your one right spot. Okay. More on this? New question? What's new question? Well, since you got a first hand there, then we'll come back. What?
19.
Didn't you just say 19?
Yeah.
Oh, look at that. So element Z has 2 natural isotopes. Z79 with a bunch of numbers for our mass, Z78 with a bunch of numbers for our mass. Calculate the atomic mass of element Z given the abundance of Z79 is 50.69. Okay. Right out of the gate on this, there's so many numbers that are very similar, letters showing up all the way. In that case, what I personally would do is try to simplify it and stop referring to them by their full names. Z79 has now become A. Z78 will become B. Okay? That can help me kind of whittle away some of the numbers that aren't useful and can help me see it. Okay? And it's just going for me personally. When we're looking at our atomic mass, the atomic mass is a weighted average. So it's going to be the sum or the average of our masses of each of those particles. Well, the mass of particle A was 78.918 AMUs plus the mass of the second one, 80.916 AMUs, and then we could divide by 2. Well, if we're dividing by 2, so hold off on those of you drawing divide by 2. If we're dividing by 2, really what we're saying is that our mixture is, exactly as Mason just mumbled, it's a 50% mixture, which is 0.5, which is really just saying 1 divided by 2, which is exactly what we just went through and did. Okay? So we're saying it's a 50% mixture. Is it a 50% mixture? No. So that means saying dividing by 2 becomes invalid, and I have to account for the weight appropriately. So the weight will go in our parentheses. I know that the weight for A is 50.69, okay? Which means this needs to be 0.5069. So far, so good? Okay. Well, the weighted average is the sum of those. So I would take 50.69 times 78.918 plus some number that I don't have times the 80.916, and I'd add that up and punch it in my calculator and get an answer. But if I don't know what's in that parentheses, I can't solve this. Okay, well, what if that first one was not 50.69 but 50? What would go in box B? 50. Because there's only two things. So if I know one is 50, the other one must be 50. If I know one is 70, the other one is 30. How are you doing that? It all has to total up to 100%. So the percent of A plus the percent of B must equal 100%. If I know A is 50.69, how do I figure out B? B will be the 100 minus that. I have to convert it into the decimal form in my equation, which is what, 40... Yeah. Except oh man. Okay. Now all I have to do is enter it into the calculator. The calculator spits out an answer, and that would be my final answer for the question. Okay? That involves a significant amount of calculations. How many of you are confident in your calculations? Ooh, okay. Well, if you're not confident in your calculations, is there a way to do it without doing a bunch of calculations? Yes, there is. Okay? You can effectively eyeball it. Okay? If we're going to take the average needs to be where? Between A and B. That's the point of an average. Okay, so my average can't be lower than 78.9 and it can't be higher than 80.9. So I go through and look at my numbers. A is wrong. It's higher than the highest atomic mass I've got. So A doesn't make any sense. Okay? B, And this, I have a really hard time with this, by the way. 79.9, 78.9, that's okay. C 80.0, that's okay. 119.93, that's too high. 79.93, that's okay. Oh no, B is lower. Man, like I said, I have a hard time with this. 79 point, no it's not.
Looks great at 0, 1.
I'm literally like, what are you? It's 78 and 79.
It's 78.9.
I thought you were saying 79.
So it looks like y'all have
So at least we're all on the same page with getting confused in the 9s and the 8s and the 0s and all that fun stuff. Okay? So we can only really eliminate 2 answers. Okay? If it was a perfect 50-50 mixture, which it's darn close to, well, it would just be the average of those 2. It would be dead in the middle. Well, I do have to do a calculation, but I can add 2 numbers and divide by 2 pretty quickly on a calculator that I don't have. But if you did it, you would get a number, and that number would be what? It won't be exactly B, so we have to be a little bit hesitant there. So if I just take the average of the 2, and this is why this question is actually a bad question, I think. A plus B divided by 2. 9 what? No. You're disgusting.
And I'm going to agree with him.
So some people can do that in their head, and that's just not nice. No, my brain's broken enough. Fair enough. You win. You did a good job. In any case, your calculator spits out this number. This is the perfect middle. Okay? Are we at the perfect middle? No. We are slightly closer to which one? We are slightly closer to the A value, which means this is my exact middle. I want to be slightly closer to A. I want the number that is slightly smaller than 79.917. 79.93 is bigger. Can't be right. 80 is bigger. Can't be right. Okay. So 2 methods, a rounding kind of approximation or doing it in your head, which I'm now kind of embarrassed I should have been able to do that. Or going through the big long calculation. You had 2 options. Okay. This is not one that I would say you could quickly and easily eliminate without the question. With just a bunch of numbers, that's really hard to just say, oh, well, that one doesn't make sense. There's nothing to really group. You could potentially pull the outliers A and D because they're both really big numbers and all the other ones are really close to each other. But it's a bit of a thin guess. Make sense? So, Brooke, Skylar, you guys okay with that? Next. So, question 2. Add 7.77 to 11.666. So we could go through, we could add this up, 6, 3, 4, 9, 1. Way to just steal the thunder. Did I do it right?
Yes.
Okay. So we can enter the calculator spits that out and go, oh, well, that then must be C.
No, safe place.
Okay. So recognizing what the question is asking is going to be the important part here. What's it asking for? It's asking for sig figs. Okay. Is really what this is asking at. Because to round, you have to know what sig fig you're rounding to. Okay? So it's really a sig fig question. So since we're doing addition, how do we track our sig figs? The least accurate, I always get precise and accurate wrong. I know I said precise, but I could have been wrong. Okay. It is precise? Okay, good. Cool. So the least precise place. Which of those two numbers generates the least precise information? 7.77, because why? It only goes out to the hundredths place. That means in my answer, I can only report to the hundredths place. Which means my number must become 19.43. Here's where the rounding now comes into play. The first insignificant digit is 5 or larger, so I must add 1, and it becomes 19.44. And the answer is E. I can talk to the tutors.
There's handouts in there that say.
Say what?
There are handouts in there that say, like, when you're adding or multiplying, what you take all of it for the answer. Like,
And they're saying it wrong?
no, I'm saying they have handouts.
Oh, okay. Yeah.
So don't ask your.
Yeah.
Get into that.
So a couple questions popped up there is number one, be careful who you talk to in the tutoring center. They need to be able to explain the rule to you. Okay? Officially, and this is something that tutors always get in trouble with, and it's not an easy job. Their job is not to tell you what the rule is. Their job is to help you find the rule, so that you don't run into an issue of, well, the tutor told me something else. The tutor officially should not be telling you anything. They should be telling you, let's find where the rule says what to do, then let's follow the rules. Okay? And they should be able to follow the rules better than you. They may not remember the rules. That becomes a challenge. That's why they should not be telling you the answer. So be careful with the tutors. They need to be directing you towards where it physically says the description on how to do it, and then work through it with you. Almost guaranteed what probably happened is that our tutors will remember not the rule for addition, but the rule for multiplication and division, which is the fewest number of sig figs, which would mean 3 sig figs in your answer. Because it is addition and subtraction, it's the least precise place. So you have to apply the rule correctly. Okay? The other comment that came out was that the tutoring center has a nice list of rules. Yeah, you know who else has a nice list of rules? Me. I gave it to you at the beginning of the semester. It's in the slideshow that's on Canvas. Just have to download it and open the file and put it on a nice slide that had all the things on it. Just saying. And our answer becomes E. Does that work for you guys? Was you? Okay. Probably because you were getting confused with somebody saying one less sig fig. Yep. Yep. So addition, subtraction is the least precise place. So one of the odd things with addition and subtraction, addition, you can increase the amount of significant figures than you started with. How could you possibly do that? That's one of the things that falls out of addition and subtraction. What happens when you subtract? You can end up with less significant figures than you started with. Okay? It's a repercussion of doing that mathematical operation with sig figs. Multiplication and division, we never lose sig figs. It maintains constant. Okay? So, answers your question? Good. Did we actually need to do the math? No. Why no? Look at your answer choices. They're all mutations of one parent. That one parent is C. All the other answers are coming from some misconception of C. We don't actually have to do the addition. We can just look at the answer choices and say, what's the appropriate way to deal with sig figs? Okay? Kind of makes sense? Next. Admit 54 was one of my least favorite questions. I thought it was stupid. and then, what's that?
Why, if you think it's stupid, why would you like put it on there? Oh.
So I initially didn't like this question because I went through and did it and didn't actually answer the question the way that I tell students to answer questions, which is, it's a chemistry class, write out the chemical equation. Potassium metal, K solid, and fluorine gas, F2. Why is it F2? Fluorine's a diatomic for our fear. Okay. Potassium metal and fluorine gas react with each other in a combination style reaction. We end up forming KF. Ooh, I don't know the phase. I hope I don't get tested on that, but we'll see. Okay. I need to make sure that I predict the product correctly. The charge on potassium, a +1. The charge on fluoride, -1. My formula is correct. If I wanted to watch out for balancing, I haven't balanced it yet, and I could go back through and balance it, but at this point, I've done enough quick work that I think I can go through and answer the question. Right? The potassium ions lose electrons and the fluorine atoms gain electrons. And that immediately is probably going to elicit, oh crap, that's that redox stuff that I really didn't understand and didn't like. Okay? Well, if you really didn't understand and didn't like it, skip it. The potassium ion or atom is smaller in radius than the potassium ion. Okay, well, I'm not quite sure what that has to do with the question, but let's go ahead and look it out. Potassium versus potassium ion. To become potassium ion, what happened? It lost an electron. Okay, what dictates size, our radius? What is our radius dependent on? The electrons. If I go to potassium versus potassium ion lost electrons, which means what happens to its size? Potassium ion is smaller. So far, so good? What does the statement actually make? Potassium atom is smaller in radius than the potassium ion. Well, it says all the right words in the wrong order. By writing it out, I can see that a little bit cleaner. B is wrong. Right? That is an absolutely false statement. The fluorine atom is larger in radius than the fluoride ion. Well, again, that doesn't really have anything to do with my chemical equation. It's a bit weird, okay, but let's go through and look at it anyway. The fluorine atom versus the fluoride ion. Well, what was the fluoride ion? F minus, right? Okay. What is the difference between fluorine, and fluoride? Fluoride gained an electron. What happened to its radius? It got bigger because it gained electrons. So F minus is bigger than F. Sorry, that should say smaller. The fluorine atom is larger in radius than the fluoride ion. No. Right, it again has it backwards. Potassium ion and fluoride ion bond by sharing electrons. Okay, so there I'm going to have to kind of pull at keywords. Bond and sharing electrons. Well, what kind of bond do I get between potassium and fluoride? It's an ionic bond. And do ionic bonds share electrons? No. Ionic bonds, by definition, do not share electrons. That's why they became ions. Okay? Sharing electrons is the domain of the covalent bond. Okay? So that really means A is the only thing left that I haven't crossed off. And in the case of a true-false kind of question, this is really what you have to do. You have to evaluate every single statement. Don't just evaluate one and be like, oh, I think that's true, and move on. Evaluate every single one. Okay? So now let's go back. The potassium atoms lose electrons and the fluorine atoms gain electrons. Well, I know I didn't like that, but let's see what happened in the course of the reaction. Okay, so if I take a look at my potassium, the potassium became potassium ion. Well, that's really K going to K plus. What happened? It lost electrons, or spectrons, as I was attempting to spell. What happened to the fluorine? It went from neutral F, F2, to F minus. How did it become F minus? It gained electrons. And if we go back and look at the statement, potassium ions lose electrons. Yep. Fluorine atoms gain electrons. Yep. That statement is indeed true. Writing out the chemical equation helps draw attention to the changes in charge as you move through the question. Okay? So if I had written out, when I first attempted this question, written out the equation, okay, and then actually interpreted the redox stuff, the reduction and oxidation, I'd be able to see that A was true relatively quickly. As soon as I hit B being false, I know E can't be right, which then means A is really the only answer. Okay. I would still check C. Why would I also check one more answer? To check to make sure I didn't get A wrong, and also to check to make sure I didn't miss a true-false statement swap in the question. Maybe there was a not. Which of the following is not true? Okay? Because if it was not true, now A is wrong. So we have to be very careful with those nots. You go back and look at the regular semester exams, I try to call attention to them. This semester, or the final exam, does not call attention to your nots. So watch out for those. Who asked that? Is that good enough? As far as eliminating answers, if I looked at this without the question, believe it or not, I would have sat right in there with B and C and tried to guess between those two. Okay? So just knowing nothing else, I would have gotten the question entirely wrong because I would have been guessing at wrong answers. Why would I have grouped B and C as my possible? They're both talking about radius. So when I read the answer choices, I think, oh, it's a question about radius. I'm going to keep my focus on the radius. If I don't know anything else, I'm just going to guess between those two. Both of them turned out to be wrong. This is why guessing at answer choices isn't always the best option. Okay? Other questions about that one? So 20, which of the following energy level changes is the most energetic? So what we're doing is looking at our electrons. Okay. Electrons exist in orbitals. Remember we had that fun little drawing where we jumped up, we did this kind of thing? Everybody remember that? And we called each of those energy levels different numbers. We called them the first energy level, the second energy level, the third, the fourth, the fifth, officially all the way up to the seventh, because there are 7 rows in the periodic table. The rows are our energy levels. Okay? So what they're asking about, which of the following energy level changes is the most energetic? So if I jump from step, not from step 2, from step 3 to step 2, well, there's an energy jump there. Okay? The difference between those is my energy. Okay? Because when we looked at our diagram, that is all energy. Okay? Well, is that a larger distance or a smaller distance than from jumping from 4 to 2? It's smaller. 4 to 2 is a bigger jump. Well, what about 5 to 2? It's a bigger jump. What about 6 to 2? It's a bigger jump still. What does that mean? Which is the most energetic? 6-2. It's the one that has the largest transition in the energies. This is why we drew those energy diagrams out, okay, or why we drew the electron orbital energies that way. It's getting you to focus and think about the energies. Could this question be made massively more difficult? Absolutely it won't be, so let's not even ask that. Does that answer your question?
46.
Before we do 46, our kind of cheat on this. Most energetic, I'm looking for the biggest jump. I would at least read some of the question because I'm looking at, I need some context. Most means biggest. What looks biggest? 6-2. Okay. Thankfully the guessing trick worked that time. 46, sorry, wrong pen. How many moles of potassium nitrate contain 8.68 times 10 to the 20th KNO3 formula units? So a couple things will get a bit dicey here. Formula units was another fancy way of saying
Molecules.
molecule. We have to call it a formula unit because potassium nitrate is
Nitrate.
not that far off. It's an ionic compound. That's why they're called formula units. Okay? But it's the same thing, effective thing as a molecule. Okay? So what are we starting, or what do we want for an answer? Just said moles, right? Moles of potassium nitrate. Potassium is K. Nitrate is NO3. Okay? What am I starting with? 8.68 times 10 to the 20th. I'm going to say MLCS for molecules of KNO3. Are molecules the same thing as moles? No. What do I need to do? I need a conversion. In that conversion, what do I know needs to happen and where does it need to happen? Molecules must disappear. Okay, it must be crossed out. The only way it can disappear is if molecule shows up where in my conversion? On the bottom. What else needs to happen? Moles needs to appear. This is the ideal situation. I do it in one fell swoop of a calculation. I don't have to do multiple ones. Do I know a conversion between molecules and moles? Yes, that's Avogadro's number. Okay. What was that number? 6.022 times 10 to the 23rd equals 1 mole. What showed up in front of moles? Guess what shows up in front of molecules? Okay. Did you just say Avogadro's number? The MLCS cancels. We'd be left with moles. It's now just a question of entering it into the calculator. Okay. In that approach, kind of calculator tips that I would use, I would take 8.68, divide by 6.022, multiply 10 to the 20th. I take this power of 10 is happening in the denominator. I can make it in the numerator if I make it negative. Okay. So these are my tricks. If you don't want to do these tricks, don't worry about it. You can just enter it in the calculator and hope for the best. Okay. I would then address this. I can simplify that to now becoming 10 to the minus 3. I do the calculation of the 8.68 divided by 6.022 times my 10 to the minus 3, and I'd have whatever my answer was. And I have a feeling if we do this in the calculator, we get 1.44 times 10 to the minus 3. 1, 2, 3, and I get 0.00144. Go back and check the answers. Okay. Interestingly enough, by looking at those answer choices, I would probably immediately focus in on those 3 as my possible answer choices. Why those 3?
Because they all
They're the same, so I would eliminate the 6 and the 9, 4. Now I would hope punching in the calculator enough I got one of those answers. Unfortunately, really what they're testing on here, powers of 10. If you can't enter the power of 10 appropriately into your calculator, you will get B or C, it looks like. Because D was our correct answer. So you do have to be aware of how to punch it into the calculator. So if you have questions on entering it into the calculator, please talk to me after class. We want to make sure we got that squared away. Questions about that one? Heather, that was you, right? Yeah. Are you good on it?
Well, this should be a quick one, but the one above it is 45. For A, B, and C, is it wrong because it's not 6.022? Or is it D?
No. That's all of the above.
Oh, yeah.
D.
So you don't need exactly 6.022.
Why do I do 6.022 and textbook shows 6.02? Because I'm somehow remembered that there's an extra 2 there. I mean, what is pi? What's the numerical value for pi? 3.14, etc. There's a bunch of numbers associated with it. Some people just remember 3.14. That's all I remember. You already listed off an extra 2 or 3 after that. Okay? I don't remember those. I happen to remember that there's an extra 2 for Avogadro's number. Okay? Which could be an artifact of me taking general chemistry. So if you have to move into 151 and 152, I think the standard is in those courses, instead of 3 sig figs, the standard is 4. 4. Okay? Whereas in 130, we tend to only run with 3 sig figs, which is why they're only reported to 602, because most calculations will only ask for 3. Okay? Did I record that? Yes. Are we good? Both those? Yeah. Number 8. A deceivingly simple looking question that a lot of people tend to kind of goof on. Okay. So when we're going through and looking at this, how do I want to set this up? Shoot. I don't want to have to do it for each answer. Yeah, we'll do it that way. Centi means what? I don't accept 100. Powers 10. 10 to the negative 2. Deci. 10 to the negative 1. Killi. 10 to the third. Milli. 10 to the negative third. Okay? None of the above is always a sneaky backhanded question or answer choice, because that could really screw us over, so we have to now actually answer the question. By going through and specifying what those prefixes meant, we can eliminate 3 answers. Because when we look at our answer choice, it's 1 times 10 to the second, which means my power of 10 had better include 2. That means B, C, and D are all wrong. Okay? Just to make sure none of the above isn't actually messing with me, okay? 1 centiliter is equal to 1 times 10 to the negative second liters. That was the whole point of that notation. Does everybody see that? Make sense? Okay. Is that what was written? No. What did they do? It says 1 liter, which means what did we do to that 10 to the second, or 10 to the negative second? We divided both sides by 10 to the negative second. And I get 1 liter equals 1 over 10 to the negative second centiliters. Well, 1 over 10 to the negative second, that doesn't look like 1 times 10 to the second. Okay. For those of us that remembered the shortcut that we talked about briefly, what did the negative mean? Do the calculation in the opposite location of where it is located. So 10 to the second needs to happen in the numerator. Is that what's actually written up there? 1 times 10 to the second centiliters equals 1 liter. Okay? For those of you that don't like that method, don't just say because it says a -2 and that says a +2 that it is now wrong. Don't do that, because we have this little device. What does that little device do? When you punch it, certain buttons on it with different numbers and different mathematical symbols, you can hit enter and it spits out a number. What number does it spit out when it says 1 divided by 10 to the -2? 100. When you take that same calculator and you punch it a whole bunch, what happens when you hit 1 times 10 to the second? Okay. So be careful with this type of conversion. It's intended to kind of trick and mislead you. Write down what you know, set it up, and work through what you know. See if you can get what you know to match what's there. If it does match, you're done. Great, everything's happy. Make sense? Who asked? Are you good? As far as eliminating answer choices here, without the question, I got nothing. Absolutely nothing. The only shortcut I've got here is to go through and say, what do those symbols mean? What do the prefixes mean? Centi, deci, kilo, and milli were all 4 prefixes that I told you to memorize. You needed to know what those powers of 10 meant. By memorizing the 100 and all of that, it could get dicey. I would stick to the powers of 10. Okay? Next. What is the percentage of water in borax? Oh, I don't know what borax is. They gave you the formula. Work with the formula. Okay? So I want to know the percentage of water. Okay, to answer this, I actually have to know what water is. What is water? Where does H2O show up in my formula? Right there at the end. Okay? So if I'm going to figure out the percentage of water, that's going to be the mass, which is really what they should be saying, mass, percent by mass, the mass of water per a mass of borax sample. Well, did they give you a mass? No. Well, how could you possibly figure this out if you don't know the mass? Times it. Kind of, sort of with the periodic table. We have to pick a mass that is most appropriate, okay, that satisfies everything. So what I will do is pick a relatively easy unit to work with. I'll pick 1 mole of borax. If I have 1 mole of borax, can I convert that into grams? How? Using the molar mass from the periodic table. Because I picked 1 mole, the moles cancel. All I have to do is total up the mass of all of the elements off the periodic table for borax. Okay? So, sodium. What is the mass of sodium? 22.99. 14, you were looking at nitrogen. How many sodiums are there? Okay. Boron. Was it 11? You should probably do 10.81. Times 4. Oxygen. Times 7. We'll address that in a second too. How many times does oxygen show up in this? But I will come back to this. The symbol shows up twice. Okay? We see an oxygen with 7 there. We see an oxygen there, but with a 10 in front. So the number of times oxygen shows up is 17. I promise I will get back to the dot. Okay? Do I want to do 16 times 17? I would argue no. I want to stick it at 7. Okay? And the reason will become more apparent in a little bit. What's the next thing that shows up? Hydrogen with a mass of 1.01 times how many? 20. Because we have the subscript and the superscript in front of it. And then oxygen shows up again, 16 times 10. I'd go through, determine what all these numbers were, and the sum of all of those, come on, pen, gets me the mass of borax. How do I get the mass of water? If I split the oxygen, it's just the mass of those last two. If I didn't split the oxygen, I have to go through and re-add everything. Okay? So by splitting it out, that can help me do the addition. Okay? So what I missed was actually where the question was, not so much probably in the calculation. Okay? So in our calculation, you just have to figure out the masses, set it up, percents, all that fun stuff. What it sounds like the question was actually asking about is what the heck is that dot? And not to throw you all under the bus, but you should all already know this because of lab. This is where that dot showed up, was in lab. Okay? Not a big deal, don't stress. All the dot means is that those two compounds are linked. Why did they not instead write it out as, say, Na2B4O17H20? What they're trying to show by using that dot is that there's really two separate compounds that are inextricably linked. Water as an independent molecule is embedded in the crystal structure of that compound. That's why the dot's being used. It's still part of the formula, but we're trying to separate it out so that we can see it in. That's it. The answer for that, I don't know. I don't have all the math. What'd you get? 47. I got 47.2, which is D. Oh, if you got A, I've got 4 or 5 D's going out of that one. So I think the answer is D. If you didn't get D, you should check that out.